And welcome back. Now we've got a number of STM32s on the board today. No, my mistake, we haven't. They're not STM32s at all, are they? Well, one of them is and the others aren't. So we're going to have a good look at exactly what constitutes an STM32 here. We're going to have a look at my PCB that I built up. You can see it there, sort of partially built. Anyway, did it work though? And more news on the USB front. I'll tell you, it goes from bad to worse to good-ish. Okay, stay tuned, a lot more after this. Just wanted to let you know that LCSC Electronics, China's leading electronics components distributor, are sponsoring this video. In the heart of Shenzhen, China, they have a 10,000 square metre warehouse with a much larger one under construction, an investment of some 500 million renminbi. With their semi-automatic machinery, they can pick our orders to have it ready in 4 hours and sent via a variety of global shipping options. As an example, for orders to the USA, Europe and Australia, we can get them in just 3 days. Try them now. Okay, last time we had a very quick look, an overview really of the STM32 blue pill, except I discovered some of the blue pills I had weren't blue at all. They were, I don't know, some other colour. And of course I've got my green pill here. This was the board that I mentioned very, very briefly, made by JCLPCB last week, and I had a go at building one, which you can see here. And that was, you know, all pretty easy and straightforward. No, it wasn't. It was horrendous. It was the worst bit of soldering I've ever done in my entire life. And I've been soldering for, I don't know, 30 years or so. But was there a success in that? Well, we'll wait and see. But even more surprisingly is that the boards that I had ordered from Chinese websites and things, only one of them, was an actual STM32. All the rest were not. They were clones. But were they any better or any worse? Now this is the thing. When I was doing I did some more testing with that prime number thing. It's totally rewritten now, okay? The prime number test sketch that we had was horrendous because it had a float in it, which one of you guys pointed out, or at least a couple of you maybe. And the loop was in a float, and that slowed things down awfully for all the processors. As soon as I changed that, they were running through it. Even the humble little Arduino clone ran through in just a few milliseconds, and the ESP32 ran through in 0 milliseconds, literally 0. I couldn't even measure it, it was that quick. So I thought, this is no good. We need something with a bit more brute force to really plug into these things. So it's totally rewritten. I've borrowed something from the internet, and all it does is literally divide each number by 2, 3, 4, whatever, to see if we can get a remainder. It's the ideal brute force crack of a prime number. So I've run it against all these, including the ESP32 and Uno, just to get a benchmark, and then these three, which quite frankly you'd expect it to be the same, wouldn't you? But no, they were not the same. Sometimes not the same by a big margin. Okay, so at the end of the day then, if these STM32s F103s are not the same, they should not really be called blue pills. They're sort of clones of a blue pill. Does that make them any better? Right, let's have a look at some of the benchmarks that I took. Right, this is the sketch that I've been using, which I borrowed off the internet. If I find the place where I took it from, I'll put a link down below. Give credit where it's due, but it's a fairly simple program actually, something you might have just written intuitively how to find prime numbers. That is, take a number, 10, and divide it by every other possible number starting from say 2 until you find that it's evenly divisible. Okay, now luckily the person who wrote this already knows that if you take a square root of the number, that's the maximum. You have to find out whether there are any divisors or not, and so it makes it a lot quicker. Not that we're bothered one way or the other about quickness, it's how quick it executes on each of these platforms. Okay, now I've done lots of these tests, and obviously it's going to take a lot of time plugging things in and out, uploading to each of these things, putting on serial monitors. So I've done all this in advance. So I'm going to plug all this in now, and then I'll talk over it later. But the thing to think about is, are we comparing apples with apples here? Well, obviously the Uno at one end of the spectrum is going to be the slowest. We know that. We don't have to think about, you know, but it's slow, but not that slow, is it? 16 megahertz, it's all right. And then of course you've got the ESP32 at the other end, and that's, we also know that is stupidly fast. But how much faster or slower are those than any of these STM32s, which are not actually STM32s at all? We got the three types of chip we got in here today are, we've got the CK one, CK32, they're all F103s, and we've got the GD32 F103s. Now, both those chips, they're fully licensed for the ARM instruction set, from what I've read. Okay, so whilst they're clones in that sense, they're fully licensed, and they're just, well, hopefully added value chips. After all, why would you choose, say, a GD over an ST32? It's something's got to be different, surely, apart from price, and the price differential is pennies, so it can't just be that. We'll talk about that later. Let's have a look at the run times of each of these boards now and see what we come up with. And we're starting off with the humble Arduino Uno, which is exactly the same as the Nano electrically, just a different shape. We'll upload this and see how many this discovers within 30 seconds. It's always 30 seconds, okay, for each board. Right, let's upload. Right, so it's starting the calculations, and now it's got 30 seconds. I'll speed this bit up. Right, there we are then. 3,850 prime numbers found in 30 seconds, with the highest prime number of 36,277. Okay, that's the base benchmark then. Let's now do a couple of the others. Well, 2 or 3 anyway. Right, so this is the result of the blue pill module that I built, well, partially built. So it's running the new prime calculation sketch, and the results here, I think you can see, are pretty consistent. Okay, 76,375 primes in 30 seconds. It's always found the same highest number. Okay, now this was compiled on the options with the default setting for optimization. So let's see what happens if I go to fastest setting, which is -03. Let's just recompile that and upload and see what happens. Right, so that's interesting actually. I thought when it said optimization fastest, I thought it meant not the fastest code, I thought it meant the fastest to compile. And in fact, the order of the options on that drop-down menu indicate that. But obviously it's found more now, isn't it? 78,680. And the highest prime number has indeed gone up. So it has actually done more work. Well, let's compare this then to the others. Right, what we're doing here is uploading the new prime number sketch to the standard, kosher if you like, STM32. Okay, and we're off. Right, so 52,438, which is, well, quite a bit slower, isn't it? So let's recompile this with the optimization on. I think we might give up then at this point. Right, so we're off. I do notice with the standard STM F103 series, you do have to press that reset button on some of the boards. Some boards start the sketch immediately after it's uploaded. Others just sit there, like this one did, until I move the jumper and then press reset. Right, 53,000. Still quite a bit less, isn't it, than some of the other boards? Interesting. Right, this one is what I've called my Calvin Klein sketch, or board, I should say, my Calvin Klein board. And we'll just see if that makes any difference whatsoever. Right, off we go. I had to move the jumper and press reset for this to start working as well, incidentally, on the Calvin Klein board. Right, 61,156 primes. That's about on par with one of the two of the others we've seen. Okay, what I'm going to do then is compile a little table, and we'll have a discussion about all this, I think. Right, so here are the results of the Ralph Bacon jury on all these boards. The Uno did 3,849. Whether that was the same as what you just saw on screen, well, it might be down to a few differences, you know, as we do it. The kosher STM32 did 52,271. These are all non-optimized. The ESP32, which I didn't show you, came up at 179,512. Yeah, I know. The Maple Mini, which also I didn't show you, was 50,078, and the clone was about 76,000 and loose change. So what does that mean? It means that the Uno's the base speed, right? The STM32, Stack Kosher one, blue pill, is 13.5 times faster than the Uno. But then again, the ESP32 is 46 times faster than the Uno and 3.4 times faster than the STM32. Not so much on the GD32 STM32 chip, obviously because the GD is running at 108 megahertz. So not surprisingly, it beat the STM32 and indeed the CK32. But there we are. So there we are. Food for thought, if nothing else. So regarding the clones then, as we're calling them, they're not really clones, are they? They're just alternative chips. But the GD32 F103, fully licensed with ARM and all the rest of it, and they're very proud of what they're doing, but it is mainly a Far Eastern component. You tend not to get them over here in the West. You can buy the chips, of course, as I've done. Now, my sponsor, LCSC, said, do your viewers know that there are alternatives to lots of components? But I mean, let's pick this one specifically. And I said, well, are they the same? Do they perform the same? Are they pin for pin compatible? You know, can you just swap one out? And, you know, I've got the PDFs and things like that. So I thought, well, what I could do, I said in a very rash moment, I could just remove one of these blue pills. I could just take that chip off and put one of these GD pills on instead. What do you think? And she says, yeah, go for it. I said, well, I don't know how easy that's going to be. Maybe I'll get a board made by your sister company, JCLPCB, this one here, and build one up in an even rasher moment, thinking, how difficult can it be? Spoiler alert, very, very difficult. Okay, so I made one, and here it is. So let's think about exactly what happened. So this was the true STM103. Okay, and in fact, if we zoom in on that chip, you can see it's upside down, but it actually says STM32. All right, now here's another one that I had. But on this chip, you might be able to see that's a GD32. Because what I've done, as you can probably make out from the absolutely horrendous soldering on there, I took that chip off, which I had to do with a hot air gun. That was all right. I mean, the hot air gun worked really well. But I didn't really know what temperature to set it to. I set it to 260 for desoldering. So I didn't want to damage anything, especially that crystal. If I damaged that crystal, it would have been a bit of a downer, wouldn't it? I then just put the other one, cleaned up the board, put the other one back on and started tacking it in. It was quite difficult, mainly because my eyesight isn't that of a 30-year-old's anymore, especially with this eye. So it was quite a challenge, and I had to actually use my video camera, there's one here that's wobbling, to actually zoom in like a USB microscope, which makes me think those USB microscopes could be a good value. So I might be looking into those. Okay, that's that one done then, and of course it did run. Well, I say of course, there was no of course about it. I mean, I was crossing my fingers, but yes, it did run. And then I built this one up. This was from a plain board. Okay, and I had all the components from LCSC supplied. And the board itself, I did not design this. Do not think I just went out and designed this board. Let me show you where I got the design from. Now this is all using EasyEDA, and as you know, EasyEDA have lots of people in there contributing their projects, and you can just take it and do what you like with it, really, because this particular board anyway, it was all share alike Creative Commons attribution. So let's have a look where I got it from. So here we are on the EasyEDA site, which is what I've used to get this board, and this is the chap. I don't really know how to say that. Is that an E in the middle there, or is it Rebus or R3bus? I don't know. Anyway, I did message him and say, did you get this to work? You know, is it any good? Unfortunately, I didn't get a response, but if you notice the license here, this bit here, CC by SA 3.0, that means Creative Commons attribution, which means as long as I say this is where I got it from, he designed it, not me, and he's made some changes, which I'll go through in a sec, it's fine. You can even use it for commercial use and everything else, which is great. I mean, that's what, I mean, really this hobby's about, isn't it? Sharing stuff, generally. So the changes he's made, let's have a look. He mentions them here very briefly. So he's got a diode between the USB power and the other power pin. In fact, if we look at the document here, let's bring this up in EasyEDA, and then you probably get a better idea. Right, so this is one change he's made here. Then he's put a diode in here between the VCC of your USB socket and the plus 5 volts. So if you have two power supplies here, that is from your USB and an additional one, you'll probably go and blow up your PC or laptop, because power will flow from 5 volts into the VCC of your USB and you could damage it. But by putting this diode in here, it blocks it, everything's okay. And the fact that it reduces the 5 volts from VCC if you don't have another supply doesn't seem to make any difference whatsoever. The other thing he's changed, which a lot of people have already mentioned, is that this R10 value has got to be 1.5K, not 10K, which most of those boards seem to have on there. I don't know why. The reference board from STM themselves don't say put a 10K in there, but there we are. The way to get around this, if you do have a 10K here rather than 1.5, is simply to put a 1.8K between PA12 pin and plus 5 volts, and then you'll get a 1.5. Does that help with the USB problem? No, it damn well doesn't. I tell you, I've tried everything, but we'll come more about the USB. What else has he done? Right, on the power supply then, the AMS 1117, this is a 3.3 volt thing. He's changed C6 to 330 microfarads and C5 to 100. I don't know why he's done that. I've not read that there's an issue with the power supply, but I suppose if you're drawing lots of current, that a low value at C6 here especially could cause instability. However, when I put the 330 in this position, the whole board died. It didn't want to know. So whether my soldering was so bad it shorted something out, I don't know, but I've taken it off and it all works well without that. And there is one other thing. There's a mistake on this schematic if you were thinking of using it. Very, very easy to correct. Let me show you. So this here is the oscillator. So you've got your 8 megahertz crystal here with your two 20 PFs. That's the clock crystal here, but that hasn't changed. But on here he hasn't put a connection from this point to ground. This here needs to go to ground in the same way that these do. Luckily on the board this particular track is right next to the ground plane, so it's just a matter of bringing a bridge really from here to the ground plane. But I used this because I didn't want any issues that were previously there. As it happened, I could have used a standard one because all the changes that he made, I never even got that far. In fact, let's just have a look to see how far I got. Right, so this is a nice close-up of the board that I eventually built up. Now let me think about what I can tell you about it. Putting the chip on, was that easy? No, it wasn't. I've got to be honest. Right. These pins are so close. Trying to get them soldered was next to impossible. And really, over to you guys. How would you solder that pin on? I was thinking, solder paste. How do you get the solder paste just on the pads? Even if you had a screen to put it on with, I still can't believe it would actually just fit on exactly. So I don't know how the best way is to get that chip on there, but eventually I did. Took a couple of goes. A couple of pins weren't soldered on, you know, it looked like they were, but they weren't actually soldered. But anyway, that went in. Crystals, these are the two crystals, the 8 meg and the 32K one. That's okay. A couple of LEDs here, which I chose different colours. And on the back, I've just done the bare minimum. This is like a an absolute minimal green pill board. So here's the area we were talking about in the schematic. These are the two 20 PF capacitors, the 1 mega ohm resistor in the middle, and that's the bridge that I had to do there. This is the ground plane here that I'm touching, and that's the track that connects the two capacitors. So I just put a bridge in there, and that was all okay. There's a couple of decoupling capacitor, put on one there, and I think one over here. I think that might be a decoupling one. That's the place for that big 330. But as soon as I put a 330 across there, the board just died, quite literally died. Well, the red LED went on very, very, very dimly, and that was the end of that. Didn't want to know, so I took it off again. And I can't remember what the rest of them are now. Anyway, so I've got to the absolute minimum that I need. So let's plug this into some power, because that's all it needs at the moment, and see what happens, shall we? Right, that's compiling. You know it takes quite a while, though, always does. I'm using the FTDI serial, USB to serial converter. My ST-Link has blown up. Yeah, I know. I don't know what I did with it, but I'll plug it in now, and USB says I don't know what that device is anymore. So that's sort of gone by the window. I'll have to look into what happened there. Oh, there we are. It's writing to the memory. Has it done it? Right, it's done it. And as you can see, we get our double blink. Now this is a different double blink to what I normally upload. It's one fast and then one very slow, just so I knew I'd uploaded something. So, and not just that, I haven't even put the headers on this one. You can see, look, there's no header pins in. I've just stuffed these DuPont wires in the holes and hope for the best. And lo and behold, woohoo, it worked. Okay, so what that means is this one here. Oh, let's take that code off again, shall we? Right, so what we've got... Oh, now the power's come out. Right, there we are. You can see it in all its glory. I know. So apart from the horrendous soldering on that chip, which really is horrendous, and in fact even the surface mount components were pretty poor. I mean, basically these ones, all the components on here are all 0603, which translated means speck of dust. In fact, I've probably got more components on my workshop floor at the moment where they sort of either pinged off the board or came out of the tweezers or just fell out of the packet, bounced on the workbench and then onto my floor, and you will never ever find them again. I mean, it's impossible. They really are a speck of dust, and these are basically too small for me. This LED that I put on here, both these in fact, even though I ordered some LEDs from LCSC as part of this sort of kit really I've sort of put together, I used 0805 LEDs, and oh, what a joy to solder. You can actually see what you were doing. Yeah, so I'm never going to use 0603s again, which is what all these are. Definitely going to stick to 0805. Now, does that mean you guys out there are going to have similar problems? No. If you've got good eyesight, so somebody not with a dodgy left eye for a start, and you're probably 20-30 years younger than me, so you can focus on things really small pretty close, then yeah, I suspect well, that's one of the hurdles that you won't have to jump over. Then you need a very good soldering iron, nice fine tip but not a pointed tip, some decent solder. I think you'd probably be able to do it okay. And if you've got those jeweler's glasses that I showed you last time, where they sit on your head, that would also make life an awful lot easier because they magnify things. You want to see them. Alright, just a sec. Right, these are what I use. Makes me look like something out of Star Wars, I think, don't you? Anyway, this bit at the front here is the nice magnifying thing. You get 5 of these in that kit, so you can go from just a little bit of magnification, I think it's 1 times, right up to something like 3.5, 4, and that bit flips up so you can see what you're doing underneath when you don't need it. But this, I mean, without these, I wouldn't have been able to do anything. These are what watchmakers use all the time. You can imagine a watchmaker trying to see all those little tiny cogs and springs and whatnot. Well, they wouldn't, not without something like this. Or, as I say, a USB microphone. That would be my next port of call, if only I could afford one. Yeah. Right, okay, so this worked, and of course it's using the GD32 F103 that LCSC sort of brought to my attention. They said, look, why not try it with that? So I have, and it works. The one that I replaced over here, was it that one? No, the soldering's too gone on that. That's I know it's not mine. Let me find the one that I did, and we'll look at that as well. Right, so this is the one where I replaced the chip. Oh, by the way, that resistor that I was telling you about, the 1.8K or whatever, that makes no difference at all to the USB. But there's news on the USB just coming up in a little while. Let me just plug this in, and we'll move on. Right, there we are. That's the standard double blink that I normally put on programs. That's working absolutely fine as well. Okay, let's think about USB connectivity and why it failed and all the rest of it. Right, so what you've got here then is part of Roger Clark's website. He's in Melbourne, Australia, and he's the guru of all things STM32, and he acknowledges that the GD32 and I believe the CK32 are all sort of valid chips. And he gives all these possible bootloaders that you can load up as part of something you just load up in the chip like you would do with an Arduino. And the one they say you should be using for the STM32 blue pill is this one here, except that no matter what I do, it doesn't work at all. So what I did yesterday, I went through these, starting from the top and working my way down on the alternative boards that I have. And I eventually hit the jackpot, really. I found one of these that works consistently every single time, and I can now upload and download and stuff via the USB port from one of these clones. So let me go and grab the board, plug it in, show you on the ports, and then we'll discuss which one it was. Right, so what happens then when you upload this bootloader? Well, first thing, if you notice right at the top here, you'll see that you get this Atmel USB device suddenly pop up and it says Maple DFU. And that's great because that's exactly what you want. It means you can use the bootloader after that. So which USB driver or bootloader is it that I finally managed to get working? This one here, this STM32 boot bin, so this one here, that one worked on all the clones. So whether it's a CK or a GD, it worked fine. Not, however, an STM kosher STM32 blue pill. So what happens is when you run it, it says, look, I found a maple loader, I've found it, I'm opening it up, blah, 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 flashing it, and I've done it. So if you want to see that working, keep tuned, and we'll upload a new sketch to that board. So what you're looking at here is the ports now. When I've plugged in the board down here, which you can probably see just behind me on the workbench, this is the one where I've replaced the chip with a GD chip, and it's come up there quite happily as maple cereal on COM3. Now, just to make sure that works, what I'm going to do is go to the sketch you see behind you, change the upload method to bootloader, put it onto the correct port, which is COM3, and it says okay, I've accepted all that, and upload. So it should find that COM3 now, no trouble at all. That one, hopefully not Leonardo. In fact, I'm going to switch that off. That's my video switcher. Right, so we're just left with the COM3 now. Compiling away, taking forever as usual. And that's it. It says it's done it, and whatever I put on here is now running. You can't see it. There it is. There's the double blink happening behind the scenes. Isn't that cool? So I'm going to put full details of this, probably a bit more in my GitHub actually this time. There'll be some information about this below the video, but if you want the full-blown picture with all the links and everything, please do go to the GitHub, because I can put a load more stuff up there and you know, section it out, make it look nice. The README will be quite large. I can put all the files up there that you need, everything. It's definitely worth going to my GitHub. Cool, so there we are. So what have we learned from this? So, well, what have I learned? And what am I telling you that I've learned? Well, I've learned that one, the clone chips, if you want to call them that, alternative chips from Asia, are just as viable as the ones that we've come to know. So STM32, great chip and all that, but the GD32 and indeed the CK32 are just as good and viable, and indeed the GD chip, the one that I've been playing about more with here, soldering on and creating my little boards with and things, they actually provide added value because they're running faster and can load a bootloader without any hassle, and well, do everything else that the STM32 can do, which I'm sure must annoy ST Microelectronics a great deal. But there we are. It's just an alternative, isn't it? And if you want to play about, I'll put all the links for LCSC as well. Now, when I ordered all this to make this board, let me just get rid of this code. So when I ordered all the components for this, I said, well, I want you know, 2 LEDs, a couple of resistors, and they go, oh, no, you've got to order them by the 50 or the 100. And I go, 50? Do I really want 50? Do I want 100? I mean, how many do I need? Well, it works out, of course, that each individual resistor is like 0.01 of a cent or something ridiculous. So you buy 100 and it comes to like $2. And believe me, as I say, I've probably got 50 cents worth of those resistors on my floor at the moment somewhere. They are tiny. So do buy 100 if that's what the minimum order quantity is. It's only a little strip. You want to see. All right, just a second. So this is the big box that turned up the other day, and inside it, let's open up a few things. Okay, as a typical example then, this is one thing I ordered. It's a 1 microfarad 16 volt capacitor SMD, and as you can see up here it says 0603, and I've got to buy 50 of them. All right, so what does it look like inside this little packet? So you get this strip of components. and it's not a very long strip. I mean, that's it. There's your 50, and all you do, as you can see, I've probably started it from one end. You peel back the little transparent cover, and those little black devices are indeed the ones that I had to solder on, and you can see how small they are. Let me just grab one out. Now, can you see that little speck on my hand? That is it. That is the tiny little capacitor 0603 that I had to solder on. I mean, isn't that just plain ridiculous? I don't know how the machines do it. And just to bring the point home a little bit more, on this workbench now, and the bit that you can see in here, that little device is sitting there. Can you spot it? I mean, when it drops out of the packet, you've got to find it, you know, and there it is, just there where the 2 arrows are pointing at it. Let me see how far I can zoom in so you can see where it is. Where it says 45 degrees at the intersection of the 2 arrows. There it is, look. There, that is the little tiny device. That is absolutely ridiculous, isn't it? Yeah, and that's what you have to solder. So I say, you need good eyesight, a steady hand, some decent soldering iron, and, well, nerves of steel, quite frankly. I'm not going to continue this board anymore because, well, it's working now, and I'm just worried now if I start doing anything else to it, it's going to stop working. But you never know, I might have another go. If anybody wants one of these PCBs, though, and you live in the UK, okay, let's get that quite clear. If you live in the UK and you want one of these PCBs from JCLPCB, you're more than welcome to send me via email your address, and I'll send you one off. FOC. Even if it's just to look at the board, because I don't want to build anymore, that's just too hard work for me, but you might want to have a go. So there we are. Cool. So I think we've learnt quite a bit really this video, haven't we? The fact that these clone chips, if you want to call them that, alternative chips from the Far East, are in fact a viable proposition for anybody thinking about building stuff, and indeed you can get added value. And even the USB bit works better on them than it does on the standard one for whatever reason. I don't know why. But there we are. Anyway, I hope you like this video. I'm going to call a halt now because it's gone on far too long. If you like it, give me a thumbs up, because that tells everybody YouTube and things that people liked it. Put the comments down below. I'll reply to those as well. If you've got any comments, observations, how I should be soldering that chip. Not that one, that one. Oh no, it was that one as well, wasn't it? I desoldered that. Yeah, the good ways of soldering those chips on. I'd love to know how you guys do it. And that's it. That's the end of the video. Do go to the GitHub, have a look at more information. Thanks for watching. See you in the next video. I hope you're finding these videos useful and interesting. There are plenty more videos to choose, and a couple are shown below. And if you'd like to subscribe to this channel, just click on my picture below and enjoy the rest of the videos. Thanks for watching.